Okay, so today we are continuing with files, and Friday we won't have class, so I will be available on Discord if you would like to ask questions. If you have questions about the exam or anything, I will try to be available for that whole hour. So if you want to stop in and ask questions about that or about the project's homework, anything like that, about the stuff that's due Friday, feel free to ask then. Otherwise, keep in mind all of those things are due on Friday as listed in Blackboard, and I will be grading them over the weekend or Monday and trying to get grades in on time. So our deadline is Tuesday morning, which means I'll hope to have everything in by Monday night at latest, but I'll probably try to get them graded over the weekend as soon as possible. So I'll try to let you know what your grades are going to be in advance if I can. So again, if you have any questions, feel free to drop in on Friday, same time, just on Discord. I'll be in the lecture lobby, and you can ask questions if you have them on any of the stuff that's due. So I also updated my calendar. I do have EI slots today, tomorrow, and on Friday morning. So if you have questions and want to have a smaller chat, I'm happy to do that either in Discord or Hangouts. So either way is fine. Just let me know. So let's dive in then. So we're going to continue talking about files today, and we're mainly going to be talking about access methods for files and then directory structures. So how we store files in directories and how those are laid out. I didn't have you do the reading for today for directory structures, which maybe would have been helpful, but hopefully it's not too difficult of information. We can go through it together. And then we have another probably lecture after the exam on protection and memory mapped files before we move on to sort of more complicated file system implementation stuff. So this is still sort of intro material. Meaning it's going to be a little bit dry still, but hopefully there'll be some interesting nuggets in here. We will have a Kahoot at the end of lecture today, so just reviewing, making sure we're on the same page with stuff. So file access methods are how we actually move through a file, how these are laid out on disk or in another secondary storage location. Basically, how can we access these as we need to for our applications? So the most simple method that we have is sequential access. And sequential access is really just the most simple thing we can do, where we read the next portion of the file and automatically advance a file pointer past wherever we just read. And same thing for writes. We write to a file and we automatically advance the file pointer to wherever we just wrote. We can reset the file pointer to the beginning of the file, or we can move backwards or forwards by some number of records. So this is what like fwrite and functions like this that you've probably used in C and C++ do, right? They have a file that we're writing to. They have a size and count of things that we're going to write, and a pointer from where we're going to write. And once we write to something, if we write again, it's going to start from the place that we left off, and it's going to write to the next part of the file. And then we have a function that we talked about a little bit on Monday, which is fseek, which allows us to reposition within a file. So this allows us to sort of rewind if we want to go back, or move forward if we want to move to a different part of the file. But really, it's just allows us to move around in this sequential file and move to some offset within that file instead. So most of the functions that we usually use in C and C++ are sequential access methods. This is commonly used for things like compilers, text editors, a lot of different applications that you end up using on your system, because what we want to do is access things in order or write things in order to a file. So anytime we're doing things sort of in order, We're not jumping around all over the place. Sequential access is going to be sort of the bread and butter way to access a file. So I'm just put here, examples, fwrite, data, size count, and file handle, fseek.
Professor, what's the difference between size and count?
So generally, fwrite allows you to write things in binary. Size would be the size of each individual piece of data that I'm going to write. Count is going to be the number of things that I'm going to write of that size. So if we have a struct my data, and struct my data has int x, int y, int z. Let's make it struct vector to make this more realistic. So we can have a struct vector, and we might have an array of struct vectors. And we would, to write those to a file, we would say fwrite vector, and this would have to be a void, so void star vector. Size is going to be size of vector in this case, and then 30 is the count. And then we'd have the file that we want to write to. So yeah, size is the actual size of the data that we're writing. Count is the number of things we're writing. And I think this is basically just like you can optimize it a little bit if you know that you're writing things of a certain size. So if it's a common sized thing like a byte-sized character, for example, we can provide a more optimized implementation of this because we know that we're writing like plain data that is just a bunch of bytes. Or if we have like word-sized data like ints or longs, depending on the system, there might be more efficient operations, ways to do this to write to the file. Whereas if we have sort of complicated data like a vector, we might need to use a more generic method that writes each of these. And then the opposite thing is reading, which reading allows us to put chunks of this size into the appropriate data structures in memory, just in case they might be spaced out or padded in some way. So instead of just reading the bytes blindly, we can read them sort of more intelligently into the data structure that we're trying to put them into or read them out of. Okay. So we have these two functions, fseek and fwrite. Just giving this as a example. With fseek, we have a couple origin points that we can use. So seek set is the beginning of the file. Seek cur is the current position of the file pointer, so wherever we're currently at. And then end is the end of the file. So this allows us to kind of jump around, rewind, or move forward as necessary. So maybe seek cur is a better example here. So offset and then start position is kind of what that means. And fseek, as an example, would be if we have this file, we want to go to maybe like we want to move a single vector back. We might do file size of vector and seek cur. So wherever I currently was in that file, like I've written 30 vectors to this file at this point. Maybe I want to edit the previous vector that I just wrote. I can seek backwards by one vector. I can write a new vector in place of that. So I can do fwrite void star vector at 9 as a vector 1 file. And this would write, I'm getting the address of the vector at the 29th position. So I'm just writing to that single, or writing that single vector. I'm still using size of vector as the size, and then I'm using 1 to only write a single one, and then I'm writing that to the file. So this would allow us to, write 30 of them, go back by 1, overwrite the last one. I know we're not changing the data here, but if we wanted to change something, this would allow us to do that. So this fseek kind of allows us to move forward and backwards through the file for sequential access. Any questions on those functions? I know these might be new for people.
Professor, with fseek, can you only move backward, or is there a method to move forward?
No, you can move. So actually, yeah, I guess offset would have to be. I want to do negative size of vector here to move backwards. So if it's negative, this offset is going to be moving backwards. If it is positive, this is going to be moving forwards. So depends on which way you want to go, but it's just the exact number of bytes that you want to move, and yeah, it'll use the positive or negative values to do that. Okay. Obviously, there are some error conditions here where, like, if we use seek set, where maybe I'll just copy this in as well, the reference positions for you, so that we have this here. So if we use seek set and we give a negative position, that's going to be a problem because we have, now we would have a, it's annoying, I can't center the table. Oh well. If we use seek set and we give a negative position, we're already at the beginning of the file. We can't go before the beginning of the file. We can't seek forward from the end of the file, things like that. So we do have to be a little bit careful that when we use these, that we make sure we don't have those error conditions. But these are, I mean, some of these are common, right? If you want to overwrite a file, you use seek set to go to the beginning. If you want to append to the end of a file, you use seek end with 0 offset to go to the end. And if you're trying to sort of replace entries or search for and replace, like search and replace in a file, would be a good condition for cur, where we would look at a record, read it, possibly write to that record if we find what we want. So we might have to read, go back, write, and then move forward in the file as needed. If we're trying to like find and replace a word in a file, we'd be looking through each byte to see if it matches the thing we're looking for, or the next couple bytes match the thing we're looking for, and then every once in a while replacing those bytes by moving backwards, writing the new bytes, and then continuing. Okay. So I will sort of leave this here as a reference for you. We may or may not get some practice with using these. I might include a short homework problem. I did want to ask too, does everyone have a, is there anyone that doesn't have their school laptop now? You don't? Okay, a few of you do not. Debating if do you two have access to a Linux system, or are you still not able to do that? It's only a few of you though, I might be able to provide something. So I would like to have a couple more coding examples on the end of the last couple chapters here. So if you have access to a computer though that can SSH, I might be able to set up an Amazon server that you can use to do the last couple projects, or the last project. So I think probably that's what we'll want to do, is to be able to have some amount of coding for those last couple parts. So I'll figure out what to do with that then, but I'll make sure we don't leave those of you out who don't have a laptop with you. It might just be a little bit more command line work than you're used to. But I will do my best to make it not too much of a pain for you. Okay, so this is sequential access. There are a couple other types that are useful in some other cases. So if we have something like a database where we have records scattered around all over storage, it might be more useful rather than having to seek through thousands and thousands of records. Think like MIDS. We have the MID system. I don't want to have to search through 4,000 records for all of the midshipmen in order to find one record for the specific advisee that I'm looking up, right? Whenever I'm looking up classes for scheduling and things like that, I don't necessarily want to have to look through all of them, compare them. I want to be able to have some sort of a way to just go directly to the place that this data is going to be. So direct access can be more efficient than sequential access when we want to do a lot of searching, and especially searching based on like a key that can somehow be turned into the place in memory where something is stored. Direct access supports fixed length records and allows the program to read or write from those records in any order. So the fixed length records part is important because we have to be able to say, instead of like fwrite above, in a direct access system, we would say fwrite data size count handle or file. And we would also need to say the position of this record. So I might say like, I want to write to the 29th record here. So in the case that I'm writing to the 29th vector, I would have this sample from above, where I basically say the same exact stuff, but I would have to also indicate that I'm writing to position 29. So this is not a function that C provides. I'm just giving this as an example of if we had a direct access method in C, this is what it would look like, is we'd have this extra 29 here to indicate that this is the record that I'm directly accessing. So I know that I have 30 vectors in this file system at this point. I know that I want to write to the 29th one, so I have to directly access this. But this allows us to then, if we have some sort of a key for our data, a way to find this in memory and to know exactly where this is on the secondary storage, I can write directly to the 29th one without seeking through the first other entries, right? All right, this is the 30th one in this case, since we're starting from 0. But I can write to the last vector entry without seeking through the rest of them. And similarly, I could write to like the 15th one in the middle without seeking backwards by some number of entries. So this just allows you to directly access records, but you do have to give this parameter. And here we would not have fseek because we don't need fseek. In this case, we just specify this is the record I want to write to that record, right? We don't have to seek to that part of the file and then write. We just say this is the entry that I want to change. So this is more efficient if we are constantly sort of reading large amounts or writing to large amounts of random, to some extent, memory. That is where we can sort of jump around memory much more efficiently than with sequential access. We can also extend this to do indexed or indexed sequential access. These are very similar. So in direct access, you're sort of specifying with this 29, you're specifying the block of memory where this is stored, which is not the most convenient thing for a programmer, right? It's not a great abstraction for us to have to know that the record I'm trying to write to is at block 29 in memory. So indexed and indexed sequential access allow you to provide some sort of more user-friendly index. So let me just mark this as direct. And then indexed would be maybe something where, I know that I'm writing to, let's say, midshipman. I'm going to write some midshipman data to this. So I'll write size of midshipman. I'm going to write one of them to the file. And in indexed, I might be able to give like a 200064 or something like that as an alpha number. So here I can then I can specify an index. In this case, the index is the alpha, and then the system will map this to the actual block in memory for me. So I don't have to know where this is stored in direct access memory. I just have to know that I want to access record number 20064. So this is a little bit nicer. It's a better abstraction for the programmer. It allows you to more easily get to things that you want to access in memory. And this is useful for things like keyed databases or key store databases, where you have like a key that's associated with everything in the database. You know, you can look up what the key is, and then you can find all of the data that you're looking for, rather than having to have this sort of direct access method where I need to know where things actually are in memory. Any questions on direct and indexed access? Okay. So let's move on then to directory structures. So this is the part that I didn't have the reading assigned for it. So we'll sort of go through this together, learning as we go. So directory structures are a symbol table that translates file names to their file control blocks. So this is just a way of organizing files in a system. I'm sure all of you are very familiar with directories, having used computer systems for quite some time. So that it should be sort of common sense, a lot of this stuff, but the actual structure, how we define these structures, sort of brings up some interesting questions of how we manage all of this stuff. So we have to support a number of features in the directory system. We need a way to search for a file. So these have symbolic names generally. You know, we name files in a way that makes sense to us. So we want to be able to search for files, usually by name, and find files that match a particular pattern. In Linux, this would be find and then the file name, I believe. It's a bit of a risky search. So find search files in the directory structure. We can provide some other specifiers as well. But essentially here we can provide a name and we'll search within the directory to tell us whether or not this exists within this directory structure. So this is the Unix command find. I'll link that in here so you don't have to search for and find. We can find files that match a particular pattern. We can create files. So if we want to add a new file to a directory, this is the Linux touch command. Does this and updates its timestamp as well. So it's also I should be doing like they need to have a better way to search for man pages. So man touch is also a very risky search. So we add a new file to the directory. We can touch a file to update its timestamp. This just creates something within this directory structure. Deleting a file, we might want to remove a file from the directory. So this can have different sort of semantics depending on what we're moving. So we might remove a file. We might also remove a subdirectory. So we can have directories that are within directories in some of these structures, and sometimes we want to remove a subdirectory from that directory. And so there are different commands depending on what we want to do. There's rm or rmdir. Both of these are commands for removing files. Rm can also remove directories if we specify the right command or the right flags for it. But these are all These are both used to remove things from the system. And we'll talk about some of the sort of complications that come along with these later on. List a directory, show contents of a directory. Everyone should know the ls command. I'm not even going to link that one. You use it all the time. Renaming a file. Because the name of the file represents contents, we want to be able to change the name when the contents or use of the file changes. So sometimes we want to change the name. You know, we often do this if I have like, if you're not using version control. I know before I learned how to use Git and Subversion, I would do things like, you know, move my file to old.cpp or backup.cpp, and then copy a new copy to make the, you know, have a second copy of the file so that if I had to go back, I could use that old copy. Now you should not be doing that. You should be using something like Git or Subversion. But, you know, in any case, there are also other uses for, you know, moving or renaming a file. So we want to be able to change the name of the file. In this case, that'd probably be like the move command is the best way to do that in Linux. And then traverse the file system. So we want to be able to move between directories. Again, everyone should know this one. CD is the way that we traverse the file system in Linux. So again, just sort of boilerplate. These are the things that we want to be thinking about when we think about how we're going to structure our directories. So, you know, if with this particular structure, how do we search for a file? How do we create files? Are there any complications with creating files or showing the contents of a directory or renaming files in this particular structure? So the first couple structures are a bit of straw men. They're sort of there to, you know, give you the indication or like give you a general idea of how this works, but not necessarily, you know, good design decisions. It might be fine in some of these cases, like if we want to provide a very simple OS for something that's not going to get used by many people, we don't necessarily have to have like a full file system structure. Like we don't need the C drive with all the different folders that it has or the root folder in Linux. If all we have is a, you know, single or a couple processes accessing different files in the same system, and, you know, little need for conflict. So there are use cases for these, but not in sort of a general purpose operating system. So this would be sort of more specialized use cases where, you know, you're writing an operating system, but you're writing it for a very specific device or something like that. So the single file system looks like this, right? We have a directory, we have names for files in that directory, and we have those linked to the individual files. So on all of these diagrams that are in the book, the directories are listed as boxes, and the files, the actual files, are listed as, or sorry, the directory, the names of files or directories in a directory are listed as boxes. The actual file nodes themselves are listed as circles. So you can think of these circles as like the actual storage on disk for that file in all of these pictures. So in a single level directory, this is the most simple thing we can support. All of the files are in a single directory, and we can't have the same name for two different files, right? Because we only have a single directory. Each file in that directory links to an actual file node. And so, you know, we can have no sharing here, you know, no files with the same name. So this is, again, a straw man, because if we have more than one user, this is ridiculous, right? We can't have two users. Like, you'd have to prepend your name to every file, which seems a little ridiculous. But maybe for a system that, you know, only has one user or that is only going to do very limited things with files, this might be okay. So the natural extension to this, because of the fact that we can't deal with users, is to have a two-level directory. So the two-level directory has a separate folder for each user. This has a master file directory that contains all of the user folders, and then a user file directory that contains each user's files. So this is, you know, a little bit better than the single level system, but still obviously has some limitations. The nice thing here is now we can see from, user 1 has a file named A, user 2 also has a file named A. In fact, all the users have a file named A. User 3 has a file named test, and so does user 1. So there, in this case, we can at least, users can name their files the same thing. But we still can't, make subdirectories within our own directory. We just have sort of, our single user directory that we have to put all of our files in. So that might make it difficult to sort of name things in a logical way that helps us understand what is actually in our file system. So in this two-level directory, we have file names that are based on the username and then the file name itself. So, we would reference files as user1 /cat /user2 /data, etc. And this is all just based off of the user's name, so we don't necessarily have to encode the username. We just have a username because we're logged in as some particular user, and that user can then access their files just by saying, so cat for user 1 accesses cat gets transformed to user 1 cat. User 2 accesses data gets transformed to user 2 data. So the operating system can sort of handle that translation of which file we're getting from each user directory based on the fact that the user is logged in. So the username plus the file name is the path name for that file, and each file has a unique path name. So because the usernames are going to be unique, the file names within those user directories don't have to be unique to get us a unique path name. Okay, so in this type of a system, how would we handle, or how would we want to handle some sort of a common utility like a compiler? So let's say we have GCC is on this system somewhere. How do we want to handle that? Go ahead and jump into your rooms real quick and chat about this for a minute or two. Okay, so I think most of you got something close to what I was looking for. So we have a couple options, right? So we can duplicate all or duplicate common utilities in each user folder. That's one possibility. The response there is that this wastes a lot of space. So we can sort of use space for flexibility. So like if we have GCC, for example, as the thing that we're trying to share, this would allow, if we duplicate the utilities, user 1 could have a different version of GCC, for example, than user 2. And this means it's still nice for us because then when user 1 accesses GCC, it's still just user 1 GCC. User 2 accesses, it's still user 2 GCC. But this does waste a lot of space, and as we have more and more users and more utilities, we're wasting more space. So the other solution is to have a common directory in the master file directory. So this is another good way to do it. So we could have like a utility folder instead of user 1 and user 2. So this saves space, but complicates the file lookup processes or procedure. Now, if I say user 1 accesses GCC, that could mean if I have a local copy, it could mean user 1 GCC or utilities / GCC, right? So it could be either one of those options if I have this common directory. And that would be the case for every single file that I look up, that it could be in one of these two places. So this is a little more complicated, but probably still worth it because we can save space on all of these utilities that are probably going to be shared between users. So I mean, on Linux, this also includes stuff like changing directories, listing files, like all of those are programs or utilities. So that means we would have to have all of those in this utility folder. So this is there are a couple options here, but I think probably the better ones is the better one is to use the common directory, just because of the fact that this does save space and does still allow us the flexibility of having a unique version. So user 1 could have their own version of GCC as long as we sort of do the more specific version first. So we would want to look for user 1 GCC, and then if that doesn't exist, we would want to look for utility GCC or like common GCC instead. Okay, so that's the 2-level directory system. We'll maybe do one more of these and then leave the rest for Monday. So the next extension to a 2-level directory is a tree directory. So the tree directory just allows us to have more links from the top level. So I'm going to make some more space here so I can put the diagram in. So a tree directory would look like this, where we have the top level. We have folders that don't necessarily correspond to names here. But we have some root directory that is the base directory, the sort of master directory from the 2-level system. And each of those directories can then link to subdirectories, and then eventually they can link to files. So we have any number of directory entries that we want to have here. We can have any number of users that can have any number of directories. Here we probably put our programs in some sort of a common folder that we look them up by. We do need to distinguish between subdirectories and files now. So compared to the 2 system, in the 2 system we have the master file directory and the user file directory. So we know that the master file directory has subdirectories that are the user directories, and then the user file directories do not have any subdirectories. So anything in the user file directory is a file. Anything in the master file directory is a subdirectory. So this was sort of hard-coded in this version, but now that we have any number of subdirectories, we might have a mix of directories and files. So like in this spell folder, spell has stat, mail, and dist. Stat is a file, dist is a file, mail is another folder. So we have to be able to distinguish between these subdirectories and files, and usually that's just a single bit in each directory entry. So, you know, within the spell directory, we say stat is a file, mail is a folder, dist is a file. And it's pretty easy to keep track of this just with a single bit. Once we are in a tree directory system, we have a difference between absolute and relative path names. So absolute path names are start with slash and specify the entire path to a file. So an example here would be if we had slash programs slash p slash list. That would be an absolute directory, or slash spell slash mail slash PRT slash last, maybe. So we're specifying everything from the root directory, the slash directory, to the end directory. So I do want to make a note here that slash is root here. Or in the case of this being like a C or a Windows operating system, this would be like C slash, users slash username slash file. Right. So this is the absolute path from where this file system begins to where the file is that we want to access. That's an absolute path name. A relative path name starts with the current directory and specifies the path from that current directory to the file. So if we are in slash spell slash mail, we can access PRT slash last by just saying PRT slash last to slash spell slash main slash PRT slash. We can specify just part of the file if we know where we currently are, and this can get us relatively to the next file in the system. So I'm going to stop there for the day. If you want to look ahead at the next couple or the next question after you're done with your exams and all the homework and everything, you're welcome to think about this a little bit over the weekend, handling deletion in this type of tree directory system. But we'll talk about that on Monday. So I do want to do a quick Kahoot before we end for the day. And I can't remember. I'm hoping that all of these questions are covered by what we finished talking about here. I think they are, but I forget exactly what all I put in this quiz. So we may have a looking forward question that'll be difficult. Let's see. Okay, we have one tricky question at the end. The other ones should be review or stuff from today. We're waiting on one more, but I know if that is, I don't think I see Ryan's name, but I know he was having some technical difficulties. So there we go. Cool. Okay. 5 questions. Which file operation resets a file's size to 0? Okay, so delete gets rid of the file completely. the file, I think, would no longer have a size at that point. So truncate is the one we're looking for here. That's it trims the file size down. You can truncate to a higher size as well, but truncate without any arguments would reset the file size to 0. It's nice work if you remembered that. Next up, in which type of locking is the application responsible for manually locking files? Mandatory or advisory? Okay, nice. So we talked about this in the context of Windows and Linux, whether you can read or write files at the same time. So this is on Windows. There's mandatory locking. So if you have a file open for editing, it is locked, or someone else tries to get the lock and you have it open for reading, it's locked. On Linux, it's advisory locking. So if you have a file open, it's up to the application to make sure that it holds a lock whenever it tries to make updates to a file, and that's advisory locking there. So mandatory is automatic, advisory is manual. Okay, next up. Which type of file access method would be most efficient for a program that appends events to a system log? Yeah, nice. Yeah, so I'd say that would be sequential, since we're just sort of starting at a position and appending at the end. Most likely, we're just pushing a file pointer each time we write to it. Index and index sequential, you're really looking for, like, having some sort of index number into a log, which an event maybe would have that if we used a time. So I could see where that might be useful, but it would be difficult to have something sparse like a log of events, since we don't guarantee that event happens like every second or something like that. Those are okay answers as well. True or false? Sister, cousin, mother is a relative path name. Okay, yeah, so this is because it starts with a slash, despite the fact that sister, cousin, and mother are all relatives, possibly. Because it starts with a slash, this is an absolute path name. So this is starting with the root file. If we didn't have this here, then, if it was just sister, cousin, mother with no slash before it, then it would be a relative path name. And one final tricky one at the end here. This is material that we've talked about these functions a little bit, and you might know this, but it's definitely a little bit the stuff I was planning to talk about at the end of class today. So a little bit difficult. Which command removes a directory even if there are files in it? Okay, yes, this is tricky. So rmdir actually requires the directory to be empty before you call that. You can do rmdir, -f or something, but in this case, the -f-r on rm will recursively, if you put an exclamation after the claim, yeah. So I think if you have extra stuff on here, then it would maybe do it. But this rm-f-r will recursively remove things from a directory and then delete the directory itself. So this is like the scariest command you can use in Linux if you have a star or a slash after that, because it just deletes everything in the system. So third place, nice work. And then second place and in the lead, I think Peanut Butter won today. So nice job, everyone. Good work today. Good luck on the exam. If you have questions, I'll be here Friday. If not, then I will see you on Monday. Have a good weekend.
Thank you.
Thanks, Professor.
I'm sorry, I do have a question.